Now we are going to solve some problems related to determination of discharge from well, that is in case of confined aquifer or unconfined aquifer. In these problems, first of all, you are going to draw the figure based on the given data. Whatever they have given in the problem, based on the data, you should draw the figure, then only the problem. Easy to estimation of discharge or determination of radius of influence or estimation of drawdowns or water depths in the wells. Now, first problem, a well penetrates in the center of an unconfined aquifer bounded extremely by a circle of radius 600 meters along which the height of water table is 8 meters. Here this is the unconfined aquifer. So unconfined aquifer means one side is impervious layer, top side is water table. Unconfined aquifer and the radius of circle, this is the radius of circle is 600 meters, that is the extreme one, 600 meters. And the depth of water at the extreme equal to 8 meters. This water table to the bottom surface is 8 meters. If a distance of 10 meters from the center of the well, the height of water table is 7.5 meters. Right? This is the center of the well. From the center of the well, 10 meters from the center of the well, have one observational well. This also having the water level is only 7.5 meters when the study conditions are established. Determine the discharge of the well. K is equal to given that is 10 power minus 4 meters per second. In this problem, they have extracted one well in unconfined aquifer and the radius of influence given, that is 600 meters, and also extreme water depth is given, that what total depth of water, that is from the water surface to the bottom layer, equal to 8 meters, and also one observational well, that is 10 meters from the main well. The water level also given 7.5 meters for the water depth in the observational well. They want to determine the discharge in this well. So we know already we derived one formula for the determination of rate of flow. Q is equal to pi k h2 square minus h1 square divided by log E R2 by R1. So here, this is the formula. Pi value you know, k value they have given in problem, that is 10 power 4 meter per second, directly substitute here, and h2 is they have given here only one observational well and another one is the one main well, and also they have given extreme conditions. But this derivation is derived based on the two observational wells, because here h1 square minus h2 square, h2 is the observational well number 2, h1 is the observational well number 1. But based on the situation, we are going to change the terms, we are going to install the given data, because they have not given always two observational wells. Based on the data, we are going to adjust and solve the problem. Here what they have given, there is no data regarding main well. They have given only one observational well, but apart from that they have given extreme conditions, that is the radius of influence is equal to 600 meters, and depth is equal to 8 meters. Now we are going to, this extreme condition is the one well, that is the one observational well, this is the another observational well. Now we are going to give relation between this is observational well number 1, this is the observational well number 2. In case of observational well number 2, the depth of water available in the well is equal to 8 meters, because this is the extreme conditions. So here, instead of here, pi k h2 square, instead of h2 square, this is the capital H2 square minus h1 square, this is the h1 square. So here pi is k value is equal to 10 power minus 4 given. Here h2 is nothing but total depth, that is 8 meters, minus this is the well number 1 7.5 meters, so square divided by log E. R2 is the extreme well, that is the well number. Based on this equation, This is the observation well number 2. Here the instead of observation well number 2 extreme conditions, that is the 600 meters radius divided by R1. R1 is that is 10 meters from the center of the well to the observation well number 1. 10 we have the answer. This is the discharge from this well, that is 5.95 into 10 power minus 4 cumex. Right here, what we observe, they have given 2 observation wells, no problem, directly substitute the values. But in this case, they have given 1 observation well number 1, and instead of observation well number 2, they have given extreme conditions, that is equal to capital R and capital H. Next problem. A 0.4 meters diameter well fully penetrates an unconfined aquifer. This is also unconfined aquifer. So that one side is impervious layer, another side is the water table like this. This is the water table, this is the impervious layer. Unconfined aquifer whose bottom is 80 meters below the undisturbed groundwater table. This is the groundwater table. Groundwater table to the bottom, the total depth is 80 meters. When pumped at a steady rate of 1. Here they have given discharge 1.50 meter cube per minute. This converts into meter cube per second. Then the 4 meters and then the drawdowns observed in 2 observation wells at a radial distance of 5 meters and 15 meters. Right, this is the one observation well. This is the another observation well. Observation well number 1 is 5 meters from the center of the main well, and observation well number 2 is the 15 meters from the main well. Then 4 meters in the observation well number 1. That means this is the water table. This is the water table in the observation well number 1. The drawdown is 4 meters. The drawdown is 4 meters. In case of observation well number 2, the drawdown is 2 meters. This is the water level in the observation well number 2. This is the drawdown in the well number 2. They want to determine the drawdown in the main well. So here they have not given any data related to the main well. They want to determine the drawdown in the main well. Drawdown means from this location, that water table to the water level in the main well. This is nothing but SW. Say this is the drawdown. Drawdown is nothing but SW, and this point to this point. Already I told you HW, head of depth of water available in the well. So they want to draw down in the well. What we can do here? So here they have not given coefficient of permeability K value. They have given 2 observation wells that are 5 distance from one well and 15 meter distance from the main well to the extreme well, and also drawdowns given. So what we know, first of all, we know one formula, Q is equal to pi k h2 square minus h1 square divided by log e r2 by r1. Here h2 square is that nothing but x, that is well number 2 water depth. H1 square means well number 1 water depth, R2 radius from main well of the well number 2, R1 radial distance from the main well to the observation well number 1. Right here, what we can do here, they have given drawdowns only here. This is 15 meters. Automatically, what is the water level? What is the water depth in the well? Because they have given 80 meters. So here 80 meters, 80 minus 15, we have the water depth from this location to this location in the well number 1. And also here they have given drawdown. The total depth of water is equal to 80 meters. So 80 minus 2, we have the water depth from this location to this location. Here also they have not given water levels in the main well as well as observation well. They have given drawdowns and also total depth. By using these 2 values, we are going to determine the H1 and H2. Here, so based on this formula, H2 is equal to 80 minus 2 square minus 80 minus 4 square divided by log E 15 by R. 15 is the radial distance from the main well to the observation well number 2. 5 is the radial distance from the main well to observation well number 1. Finally, we got this value, that is the coefficient of permeability K equal to 2.84 into 10 power minus 4 meters per second. Once we know the coefficient of permeability, they want to draw down in the main well. How we are going to determine the drawdown in the main well. Already I told you, you are going to select any two conditions, that is observation well number 1 and observation well number 2, or well number, that is main well and observation well number 1, or main well and observation well number 2. Based on the given data, you are going to select the conditions. Here they have given, they want to draw down in the main well, because we are going to consider one is the main well, another one is the observation well number 1 or observation well number 2, any one is correct. So we want to determine the drawdown. So we know the total depth of water is equal to 80 meters. The water depth in the well, main well is, let us consider, that is known as HW. That is the main well data. Main well data, we know the HW is the water available in the main well. H2 square minus HW square divided by log E R2 by R1. Instead of well number 1, here they have taken main well. We know well number 1 and well number 2, but we want to data related to main well. That's why here they have taken HW. HW is the water depth in the main well. Right? HW square minus H2 square minus HW square divided by log E. R2 is the extreme, that is the well number 2 to the RW is the radius of the main well. Right? Here they have given pi value, we know discharge is given. This is the discharge, and pi value we know, and K value already determined here 2.84 into 10 power minus 4 meter per second, and H2 value, that is 80 minus 2, we have 78 meter square, minus HW, this is the unknown, divided by log E, that is the well number 2, radial distance 15 meters, and diameter of the main well is 0.4 meters, the radius is equal to 0.2. 15 divided by 0.2 here. HW is nothing but the distance from this point to this point. Once we know the HW, they want to determine the drawdown from this level to this level. So 80, total depth 80 minus HW, we have the drawdown in the main well. Here, this is the drawdown in the main well equal to, SW is equal to 80, is the total depth, minus depth of water level in the main well, depth of water is equal to 69.82, we have the 10.18 meters, this is the drawdown in the main well. And one more problem, this is related to confined aquifer. So any problem, first of all you are going to draw the figure, then only you can understand how to solve the problem by using this derived equation. Because some cases they have given directly water depths in the main well, observation well, as well as another observation well, but some cases they have given drawdowns. So because of that, first you draw the figure based on the given data. So here, this is one more problem. A fully penetrating well of diameter 0.4 meters is drilled in a confined aquifer. Confined aquifer means one side is impervious, another side is also impervious. This is the one side, this is the another side. Thickness is equal to 2.5 meters. If the steady state drawdowns at 10 meters and 15 meters are observed to be 2.5 meters and 0.5 meters. That means two observation wells. One observation well is 10 meters from the main well, the drawdown equal to 2.5 meters. Another observation well is 50 meters from the main well, the drawdown equal to 0.5 meters. Here they want to determine the discharge, K is also given. So what we have derived for the determination of discharge, that equation is Q equal to, instead of this one, 2bk pi H2 minus H1 divided by log E R2 by R1. But here they have not given water depth in the observation well and water depth in the observation well number 2. Here they have given drawdowns. This is also given drawdown. So here, instead of that, and also they have given depth of the basin. Thus, that equation can be modified like this: 2 pi KB S1 minus S2 divided by log E R2 by R1. S1 they have given drawdown 2.5 meters, and S2 also given 0.5 meters, and R2 also given that the radial distance from main to observation well 2 is 50 meters, and R1 is also given that is the main well to the observation well number 1. All values substitute here. Finally you have the 19.52 into 10 power minus 3 cubics. That is the discharge from that confined aquifer. And last one more problem. This is also related to confined aquifer. A well of diameter 30 centimeters fully penetrates a confined aquifer. This is also confined aquifer. Confined aquifer of thickness 15 meters. This is the thickness from this point to this point is the 15 meters thickness. When pumped at a steady rate of 30 liters per second. So here that converts into meter cube per second first. Discharge is meter cube per second. And the drawdowns observed in well at a radial distance of 10 meters and 40 meters are 1.5 meters and 1.0 meters. Here also they have given two observation wells. One observation well is 10 meters from the main well, drawdown is equal to 1.5 meters, and another observation well is 40 meters from the main well and drawdown equal to 1.0 meters. Compute the radius of influence, the coefficient of permeability and transmissibility, and drawdown at the main well. Here also they have not given K value. Here they have given two observation wells and two drawdowns, and also they want to determine the drawdown in the main well as unconfined aquifer. Based on the derived equation, we know one formula. Discharge Q is equal to 2 pi Kb S1 minus S2 divided by log E R2 by R1. So in this formula, we know values of B is given that is 15 meters, and S1 is given drawdown 1.5 meters, S2 is given drawdown 1 meter, and radial distance to the observation well number 2 R1, R2 given and R1 also given. You substitute all the values, only unknown is K. Here by solving this equation, finally K value is equal to 8.8 into 10 power minus 4 meter per second. Once we know the coefficient of permeability of a particular confined aquifer, then we are going to determine the transmissibility. Transmissibility, we have one formula, transmissibility T equal to coefficient of permeability into thickness of the confined aquifer. Thickness of the confined aquifer they have given, that is B equal to 15 meters. So here transmissibility T is equal to B, thickness of the confined aquifer 15 meters into K is determined here 8.8 into 10 power minus 4. We have this is the transmissibility meter square per second, 1.3 to 10 power minus 2 meter square per second. Now we are going to determine the drawdown in the main well. As earlier case, we are going to consider two wells. One is the main well and another one is the extreme well, that is observation well number 2. So in these two wells, the formula is modified like this. Here Q is equal to 2 pi bk and SW, that is the main well drawdown, minus extreme well, that is the well number 2 drawdown, that is 1.0 meters. The corresponding radial distances are provided here. Extreme, that is well number 2, radial distance is equal to 40 meters, and the main well, that is the diameter is equal to 0.3 meters, radius is equal to 0.15 meters. Finally we have the drawdown here, SW is equal to 3.02 meters. Here we have directly get the drawdown of the main well, because here they have given number 2 as well as observation well number 2, because we have directly get the value of drawdown. Then they want to determine the radius of influence of the main well. So for the determination of radius of influence, here we are going to consider, I told you, based on the situation we are going to select the wells. If we need the radius of influence, now we are going to select the one is the main well and another one is the extreme conditions. Extreme condition drawdown is equal to 0. Once you see the figure here, this is the water table. So if the touches, in case of well number 1, this is the drawdown 1.5 meters. Observation well number 2, this is the drawdown, this is 1 meter, this is goes on, touches the water table, the drawdown is equal to 0. Where the drawdown is equal to 0, the radius is equal to capital R, that is from the main well to the, where this radial line touches the water table. This point to this point is capital R and the drawdown is equal to 0. Because here as per our formula, here 2 pi bk, here SW minus that is the drawdown at a radial distance of r, so that is 0, so that 2 pi bk SW divided by r is the extreme conditions, that is the radial distance from the main well to the where the water table touches the, where the radial flow touches the water table. R2 is the main well radius. Here 2 pi into b, thickness of the confined aquifer 15 meters. So K already we determined here 8.8 into 10 for minus 4, and SW also determined here 3.02 meters. So divided by log E, R value is unknown, that is the radius of influence, and diameter of the well given 0.3 meters, that is divided by 2, radius 0.15. Finally we have the radius of influence for a particular this confined aquifer is equal to 634 meters. So these are the problems related to the confined and unconfined aquifer